I guess now I'm going to have more visitors. Yeah. But anyway, thank you for double introduction. I'm really thrilled to be here to basically talk about what we are doing at NASA in collaboration with FAA and many industry partners about how we can transform the airspace operations to enable the new entrants in the airspace, particularly starting with drones. So this is current airspace operations. I'm sure you've seen some of these pictures from our previous talks. We also have an online video for day in the National Airspace System for about a minute that shows how the traffic actually moves and nothing happens in the night, and how it's East Coast wakes up and then West Coast wakes up. If you're interested, you can check that out. But bottom line here is there are 50,000 operations. Each operation is either arrival or departure. At a time, there are about 6,000 at peak. And there are 3 bottlenecks in the system: gates, runways, air traffic controllers, workload, and the 4th bottleneck is weather and the predictability of the weather. But fundamentally, in the system itself, there are 3 bottlenecks. So if you start to look at the future and say, well, what's happening in the sky, what's incoming, you will see a bunch of new entrants. So we have drone operations going to happen in the sky. Then we have urban air mobility. You see a lot of talk about urban air mobility, on-demand mobility. You see those drones there. Then we have supersonic at the upper airspace. You have commercial space, and then orbital systems that will go in the LEO and GEO airspace. And fundamentally, this is the current airspace right now. That if you are familiar with classification of airspace, A, B, C, D, A goes up to from 18,000 to 60,000 feet, and CD relate to the type of airports they have, and G is uncontrolled airspace. And the interesting part of the Class G airspace is because when it says uncontrolled, that means nobody provides services. So that's how we started to look at a new model for doing air traffic management. As I said before, the 3 bottlenecks in the system are gates, runways, and air traffic controllers workload. Now, what's interesting about drones is drones don't use gates and they don't use runways, and we wanted to break the 3rd bottleneck in the system, which is the workload. And that's how we started to look at the Unmanned Aircraft System Traffic Management, or UTM. And I'll talk a little bit more about that. Then we realized that it applies here, it applies to the nascent industry, urban air mobility, on-demand mobility, as well as the high altitude where there are no services provided by any air navigation service provider in the world. And there are some subtle differences between these two, and we'll talk a little bit about that as well. So this is what started to happen. If you look at the Teal Group's forecast that they did for FAA, by 2020 you will see about 800,000 unmanned aircraft systems in the sky. Each one of them will operate multiple times in a day, and millions of vehicles will operate. And you compare that with the 50,000 operations that happen today, you will quickly realize that the current system will not support these operations. So we need, again, a new way of doing things. Current system is, how many of you are pilots here? How many of you are controllers? Air traffic control pilot, okay. All right, so current system, as you know, those who are pilots, is based on clearances. If you fly in a controlled airspace, everything gets through a FAA system. Air traffic controller has to approve every changes to trajectories, which is speed, altitude, heading, anything you had to change has to be approved, so that that system has a complete awareness of where that particular aircraft is and everybody else around that. So what we decided to do is we need to maintain the situation awareness. We need to keep the safety in the airspace, but without creating this bottleneck for air traffic controllers. How do we do that? So we introduced new architecture. Fundamentally, we said FAA still has to be regulatory authority or any other air navigation service provider who can provide any constraints or directives. So these directives could be: President is in town, you need to clear the airspace, or there's search and rescue, you need to clear the airspace, or any other constraints that they want to impose on the airspace. But by redistributing the responsibilities to something we call USS, which is US Service Supplier, that allows you to take the care of the responsibilities that are typically done by air navigation service providers for the manned aviation. So we created FAA's role here, which is Flight Information Management System, mostly to connect with the regular rest of the national airspace system and provide directives, understand any requests or deviations. And the operators work with the service suppliers. In some cases, like if you have a fleet like Google or Amazon, you could be operator and service supplier, both one and the same. But in some other cases, you could be operator and you could subscribe to service suppliers. And there are a number of service suppliers that emerged. We'll talk about that. And there are data providers, weather, terrain, surveillance, and such. The service suppliers provide basically information about either trajectories, any planned operations, and any changes to the operations, or based on the missions and the conditions that they see. One of the fundamental differences with privatized air traffic management that you see in some of the parts of the world and here is there are multiple service suppliers. So that's one of the fundamental difference with this architecture and a privatized kind of air traffic management. This allows us to have a number of service suppliers, and they can do a number of vertical integrations based on their customer needs, but you can subscribe to anyone you choose to. There are a number of them already. AirMap, there is Skyward, there is Google, there's Amazon, there is Andhra, there's about 12 of those already in existence. So fundamentally, we changed the way airspace operations could work in the future, starting out with this drone traffic management. And one of the first contributions was this architecture and roles and responsibilities division. It sounds trivial, but this set up the basically main impetus as to how we can go about enabling these operations without overburdening the current airspace operations as well as air traffic controllers. So that's a pretty tall order to try to change all that at once. As you know, aviation enjoys the highest safety record in this country, and you want to keep that. And there's a lot of technology options and lots of discussions about how we can go about doing that. So we decided to chop those into 4 technical capability levels and demonstrate first capability level and the national campaign we did with the 6 FAA test site. We demonstrated the data exchange model, how that actually they interact with each other, how the operators plan their trajectories or areas of operations and interact with each other through standardized protocols. So fundamental shift here is basically share and care environment rather than one entity having a centralized view of everything and approving your changes or your plans to enter the airspace. Then the second one starts to go towards beyond visual line of sight. So the first one was the basic architecture, roles, responsibilities, data standards. Second one was going beyond visual line of sight. Now, as soon as you start to go beyond visual line of sight, then the questions come. How do you make sure that you are where you said you are going to be? So that's when the tracking starts to become very important. Detect and avoid and other capabilities. Not only you want to plan and you want to stay away from each other at the planning stage in 4 dimensions, but then you also want to make sure that you track. And I'll talk a little bit about the lessons learned from that. Then the third one we finished a few months ago, and that included manned aviation and unmanned aircraft operating in the same airspace in the vicinity of each other, and to see how we will interact with each other, what kind of systems for detect and avoid we need, what's the specification or requirement on them. And the fourth one is, now we are planning for that, which will happen next year, or actually 2019. And then the idea there is to use the urban airspace to see what happens in the tedious urban environments where the GPS is degraded and so on and so forth. All this we work through in tight collaboration with our industry partners and FAA. The idea here is to promote collaborative innovation rather than NASA only doing their own thing. So this model has worked really well because it allows us to think beyond what we only know and can do and exploit capabilities that industry bring together. Now, that's important in itself, and it will transform the capabilities. But as you start to see urban air mobility pictures, animations, all kinds of things that's out there, and vehicle developers, then you quickly realize that in order to enable those operations, we also need to worry about air traffic management or airspace operations. So there are fundamental bottlenecks here and the barriers that are being worked at, the battery and electric propulsion. Well, we are also working on airspace management and air traffic management. And here also, again, if you have to have person involved in the loop for every takeoff clearance and every landing clearance and every deviation, this model will not scale. So the idea again here is to use this automated system, one that takes advantage of cooperative nature and communication among operators as a foundation to scale these operations. Then the third layer, you start to realize, okay, not only that, you're going to have drones 400 feet and below, you're going to have urban air mobility that could go up to 4,000 feet. There will be places where urban air mobility will interact with the manned aviation, the current manned aviation as we know, and there will be places where urban air mobility vehicles will interact with the drones. And when you start to look at these drones, they are going to basically need to not only interact with each other, but they're going to have to interact with these larger vehicles. So we started to look at how best to interoperate among each other, again using the same type of data standards that we talked about before, and application protocol interfaces that define how you share and care information about your intent with each other. Now, not only these guys will have to interact with each other and stay away from each other, but they will have to stay away from drones and vice versa. So Jeu, who is Dr. Jeu Zhang, he's also working with us at NASA. He's working very closely with me on this. So Jeu will answer all the hard questions, by the way. So then our goal fundamentally is to how do we actually scale the entire airspace operations and make it better for everybody. So of course we have been focused for the last 35 years on improving the current manned aviation, reducing delays, increasing capacity, making the flights more efficient, and so on and so forth. Then we started work on drones. We're working on urban air mobility, but there are also opportunities coming up in the high altitude operations, which is 60,000 feet and up, where Google Loon, Facebook Aquila, Supersonic, and other vehicles will operate, and there are no services provided by any air navigation service provider at the moment. So this is another opportunity where we can actually look at that airspace and say, how can we transform that to enable the operations in a much more economical way. Everybody wants ubiquitous air operations, more affordable, economic, and such, but at the same time, they all want access, they all want scalability, they want safety and efficiency for every operation. Today, what happens if there's commercial space operation that takes off on the East Coast? Some of the JetBlue flights had to take detour or wait to take off. And so it impacts them negatively, and the fundamental idea here is to figure out how we can enable all of them in a much more interoperable manner, much more predictable manner, and give access to everybody that's needed and scale to the future demands that are necessary. It took me 2 hours today from my home to Oakland this morning, and I was worried that I was going to miss one of my previous talks. Ended up going there on time, but if we had transportation, urban air mobility transportation, it would have been much easier on me. Although I have to say I was able to finish 2 telecoms in that, so that was not a bad thing. But fundamental model here is flexibility where possible and structure where necessary. That's the mantra we follow. Current system is based on structure because it requires certain level of predictability because automation is low. Now moving forward, we want to offer operators as much flexibility as possible, and then structure is only when you need to create for safety reasons or security reasons. And we redistribute the responsibilities. In a way, this UTM characterization or the construct of UTM, which we'll talk a little bit more, stays in the middle, and then the connection, then the responsibilities are divided up between aircraft, the air navigation service provider, support services, and the operations center for any fleet management type activity. And they will do the trajectory planning, they will do some of the scheduling, routing, and such. And the aircraft can do the last and first 50 or 100 feet if you're taking off and landing, or if you can do self-separation in many ways. And the separation is a topic of discussion who actually gets to do it or what is the best way to do that. But one of the options is to relay the separation responsibilities on the vehicles, and then different flight rules that will allow you to get to the capacity we need. And there's always going to be a question of demand capacity management and contingencies. We'll talk a little bit about that, where you may have to have air navigation service providers come in the picture. Here is an example. It's a little bit tedious slide, but I'll give you two use cases where this becomes important. First is, let's take an example of urban air mobility. For those who are pilots here, they recognize that every general aviation aircraft has to have a reserve fuel, roughly 30 to 45 minutes, depending on where you operate. Now, these urban air mobility vehicles their basically stage length is about 30 minutes, so they cannot carry another 30 minutes of reserve fuel. That will be too heavy for them. Now, the challenge then is you have how do you meet the intent of the requirement of the reserve fuel while maintaining the safety of the operations? What happens if you have a bird strike when you are in flight? Or what happens is high winds and all of a sudden everybody has to detour. So how do you meet the intent of that requirement? The intent of the requirement is really to make sure that you have alternate landing location when you can land at the primary location, which happens many times. In this case, then fundamentally you need a connected system. So let's imagine you have a bird strike. Once you have a bird strike, you say, well, what am I going to do? You have three decisions: continue, go back, or land at the nearest spot. If you want to land at the nearest spot, then you need to have a trajectory in mind, and you need to have information about where is my nearest spot, along the route that I was going. So that could be static, but you need to know the status of that landing spot. You can't be going from parking lot to parking lot figuring out where to park, right? So if you are low on fuel, particularly. So the idea is to get that information, and if there's too much density there, then the system has to be connected such that the other operations can be moved out of the way. So that's one. Or there could be another situation where the vehicles are experiencing high winds on that. So that particular landing spot is not safe for your vehicle to go and land because the winds are so high. Then you need to know that ahead of time before you go there. So this really requires that you have a completely connected system. Autonomy is important to make those decisions, but at the same time you need information about the characterization of the resources that are available, information about your own vehicle, what's going on in the airspace and the other users, and am I going to compete with them, and what's important for the fleet management. So you may end up going to a vertipad and land there and figure out, oh, there is no maintenance facility available here. If I would have just gone on the left side, there was a maintenance facility. So this really requires that the whole entity works as an enterprise through the connected system, and the decisions are made to optimize what's at stake. So fundamental research still needs to be done here. Obviously, what is the right level of autonomy that you want to put it out on the cockpit and onboard automation, and what kind of connections we need to have with the rest of the system, and how do you get that level of information and resiliency to safely land if you have trouble. Aviation is all about managing the unexpected events. So that's sort of the fundamental idea here. How do we then get to the entire airspace operations to do the same thing with what we have been pontificating for the last 25 years, and now we have an opportunity? What are those tenets or the principles that we would like to see airspace grow into, so that we will not have to worry about the things we talked about before, which is the bottlenecks of workload and increase the affordability and scalability and efficiency of the operations. So fundamentally, we are looking at a cooperative cooperative airspace operations where every operator that enters shares the intent with each other. So it's a share and care type environment through prescribed digital data exchanges among operators through standardized protocols and interfaces. It's connected and integrated air-ground, maybe cloud services, leveraging service-oriented architecture rather than depending on a singular entity like air navigation service supplier to provide all the services. So we can get those services from third parties through competition and allow us to accelerate the transformation. Now clearly, you cannot change the airspace operations overnight all at once from left button to right button. So you had to go into stages. So we started off with low altitude, small UAS, the UTM kind of construct where the services don't exist today. We are also working on this construct where the services don't exist today. We are beginning to work on urban air mobility, where these operations will also require to be scaled at very high density. And I got 5 minutes. Okay, good. And then we'll be working on space traffic management as well. And if you are interested in collaborating with us or working with us, by all means, please let me know after the talk. Okay, this is a really good screensaver. Just kidding. The fundamental thing here is the current operations. Everything is done by all FAA. Now we're trying to migrate towards UTM-inspired ATM, where some of the services are provided by third parties. Well, two things I want to identify here. One is very little interaction happens among third parties today. Human is at the epicenter of all information integration, and we're trying to break that to saying automation should be epicenter of all information exchange. The users will cooperate with each other, and automation will address off-nominal conditions and contingencies like the bird strike and such that we talked about. That's a very tall order. To get to the same level of safety and resiliency and efficiency, if we want it to scale further, then we need to see these things happen. And those are not yet proven. If you want to get to that level of sophistication, we need to get to the automation that's very powerful to handle those contingencies. Now, how do you go about doing that? You don't have to go to New Zealand if you don't want to. You can actually go to Hawaii. Clearly you're not going to start in New York City. The Hawaii, every island is like 30 to 70 miles or kilometers from each other. So there are places where you can test this. This is another example. Bottom of the Grand Canyon right now, deliveries happen on the Mule. You can try autonomous aircraft there. Boats are used in some cases. So these are the places where you can start trying these new type of autonomous operations and get to the point that I mentioned before, the same kind of construct. So fundamentally, we really want to get to the next level of airspace operations, but we really require substantive algorithms, sensors, and test environments, as I mentioned before. This is my last slide. So we feel that the change is real right now. There's a pressing need to get to the different ways of operating or enabling these operations, because the current system will not scale up as good as it is in terms of the records of the safety and efficiency. We feel the sense of urgency. There is a lot of money going on into the drone industry and urban vehicles, particularly electric ones. Billions of dollars are being spent, but without this kind of characterization of airspace operations, it will be very hard to enable those at the scale that we are all imagining. So we follow the build a little, test a little approach, and then deploy. Obviously, there are a lot of research issues, but real goal is to cross the finish line and not continue the research forever, but really figure out the products that will enable these operations to the highly scaled need that exists today. Here is my last slide, so the timekeeper can take a deep breath here. So the idea here is basically we want to embrace the new aviation, innovation in aviation, but at the same time we have to figure out how to maintain the safety of the operations that we all enjoy. I used to put my name in the back, down below, and the people in the back couldn't see, so I put it up top. It's not like I'm important as compared to NASA, but it just the human factors. People started complaining, I can't see your name or email address. So feel free to shoot me an email, and that's my last slide, pretty much.
I just wanted to get your thoughts on the drone-related things in the FAA reauthorization bill that was just passed through, and do you feel like that's enough? Are you encouraged by that, or are we still waiting for more?
Well, I think there are two things here. One is research, and one is operations. And there are two sections in the FAA reauthorization. One calls out for, I think, UTM pilot project, and second calls out for UTM service and its implementation. I think those are really good starting points for where we are right now to get the operations going in the very near future. So, is that enough? I'm not sure that's enough to get to the urban air mobility clearly, and that might not be enough even for the entire UTM landscape. But after we have the UTM TCL4, the technical capability level 4 testing, and the UTM pilot projects, will have a little bit better idea what's left, and we can talk offline.
So I wanted to understand a little bit about the scope of the work that you're doing on UTM policies, etc. So is it more restricted to the United States, or is there a broader, intergovernmental effort, worldwide?
Yeah, it's a great question. Jehu can actually talk to you a lot about that too. But it's not just United States. Clearly, we are focused primarily on the United States, but we have a work group for UTM and actually upper E traffic management at ICAO. ICAO is, for those who don't know, International Civil Aviation Organization, which is a UN entity that's focused on harmonizing the aviation-related things across the globe. So there are two work groups, and they're harmonizing UTM constructs across the globe. We also have seen very nice efforts from Korea, KUTM, and there's Japan, JUTM, there's Singapore is doing UTM. New Zealand, I think there are a number of countries, France, there are a number of countries that are really interested in UTM. Some of them we are very tightly collaborating, and it's been a good effort that has seen a lot of sort of harmonization across the globe. Jehu, you want to add anything to that?
Yeah, we also have tariffs.
All right.
PK, you've been working on this for a long time, perhaps longer than almost anybody. And I was wondering, what have been surprises for you? Things that worked better than expected, worse than expected?
The things that worked better than expected, to be completely honest with you, the collaboration among each other and the industry, and how we were able to pull it off. A lot of times we see IP issues and things like that come in the way, but in this case, that was really awesome to see people coming together to participate in the test and come up with the defined standards. We did work groups through NASA, and I was a little bit shy whether that's going to work very well or not, but it seems to work pretty good. Surprises wise, the vehicle and their capabilities themselves is an interesting thing. I'll give you three examples. Can you hear me off in the back? So the microphone fell down, but I'll give you three examples. One is when we're doing testing in Reno. Reno is 5,080 feet, and some of the vehicles said, oh, we can go beyond visual line of sight, no problem. With the battery, 5,080 feet, 98 degrees, headwind, strong headwind, and you can barely creep up from here to there. So those who thought that, the vehicles are capable, that's not. So we have learned that lesson in manned aviation for a long time. Some of you, like you, have done that kind of testing in 3DR. But some didn't know, right? So they had to understand the environment in which you operate has a significant effect on the type of design and characterization of your, time of operation and such. Second example is also in Reno. Actually, there was a lot of updraft, and the fixed wing vehicles with low wing loading could bounce up and down 200 feet, which has implications on how close you let them fly with the manned aviation. Third one is when we were doing tests in the, there were 5 or 6, unmanned aircraft system in drones in the airspace at the time, and then the Piper Cup takes off from, and then we thought that even though we said, doing testing, don't come here kind of thing, they got curious, I suppose, and then they started to come towards the test range that we were operating. And then we got really nervous, UTM and the radars, and picked it up and gave alerts to everybody and say, you got to basically land. We tried to contact the aircraft, no radio, no beacon. So as I was saying before, aviation is full of surprises. You need to be able to handle the situations where you just need to basically go and land, you know. And those are some eye openers for some people that had never practiced aviation. The good thing about drones is it's democratized aviation in many ways. So yeah, you may have taken courses at Berkeley and other places, but then you actually didn't never flown before. If you're not pilot, you don't quite have the same level of understanding of how the impacts of environment could play, you know. So those are some interesting things that we discovered, and we're discovering a few more, like the short range communication, how close we can actually let them fly, what's the dropout rates, and yeah, so those are the things we learned. We have a bunch of, by the way, those who are interested in our papers, those are all documented lessons and things. utm.arc.nasa.gov, there's a document section. There are probably 60 papers by now, publications that you can, from concepts to field test results and lessons learned, all kinds of interesting things you'll see.
Can you say something about ADS-B out, how it's used in general aviation, and if it might be applicable to drones?
I think Jehu is in a little bit better situation to handle that question. Jehu is running our CNS, communication surveillance work group, and he probably can answer it better than I can. I can try, but I think Jehu would have a better answer.
Sure, we've been working with FAA about this issue mainly because ADS-B it plays pivotal role in manned aviation. It's mandated for controlled airspace in 2020. So current thinking is drones can perhaps equip to listen ADS-B out messages from the manned vehicles, but whether they are able to or should be broadcasting at all, that's still a subject of discussion. And 10.9 is really out of the question, so we're left with a UAT. So there's ongoing discussions about is there a way to utilize that. The bottom line is, though, ADS-B type of mechanism is very effective if the security is built in. Right now, ADS-B doesn't have built-in security. That's an issue. So in the future, we're working toward such secure system that may function like ADS-B with the drones listening in mostly.
There are some papers that some of our research is also on that site if you want to take a look at it. Thank you.
Thank you so much. Thank you.